So good afternoon, everyone. My name is Hyun-Yong. I'm a postdoc working with Professor Naoki Kawashima in ISSP. Today I'm very happy to introduce our recent work, and especially exactly 3 years ago I came here and I got the job here, and here I am today. So yes, so I'm quite happy. And yes, this is the title of my talk today, and you can find some more details in this archive post, and then also fortunately it has been accepted in PRL, so you can find this in PRL soon. So yeah, if you find some interest, then please find this paper. And these are all these are my very brilliant collaborators, and then especially for this work, Okubo-san and Kaneko-san and Naoki-sensei worked together with me. And then, so here I am here. So, yes, so. And this is the outline of my talk. So, first I'd like to give you a very short introduction to the Kitaev honeycomb model. And then maybe I will skip the second part because many speakers already introduced a very nice review on the tensor network. Then I will discuss our main result. Then I will summarize the talk. So let me start. So this is the Hamiltonian of the very famous the Kitaev honeycomb model proposed by the Kitaev. So in this model, we assign the bond-dependent Ising-like interaction. So for example, on this red bond or X bond, we only assign the sigma XX interaction, and Y on the Y bond only the YY interaction, and Z bond only ZZ interaction. So this bond-dependent interaction brings us some frustration. And also in this model, there is a very important operator, the so-called flux operator, which is defined here, so WP. And the site number 1, 2, 3, 4, 5, 6 are specified here. And this operator has only plus or minus 1 eigenvalue, and then we call this flux number, or also we can consider this as an absence or presence of the vortex on the placket. So if it has a minus 1, then flux is on the vortex is on this placket. Then one can also easily show that this flux operator commutes with the Hamiltonian regardless of the placket. Therefore, there are tons of this well-defined quantum number, flux numbers. Therefore, using this combination of the flux numbers, we could sectorize the Hilbert space. Therefore, we can reduce the Hilbert space of our interest. So this is a very important property of this model. Then, in his original paper, Kitaev fractionalized the spin operator into the 4 Mayonnaise fermionic operator in this way. Then this, for example, the sigma XX interaction becomes the 4 Mayonnaise fermionic operator. And interestingly, also one can show this BI, BJ operator also commute with the Hamiltonian. Then we could replace this BI, BJ as just a number. Then Hamiltonian becomes this very simple non-interacting Mayonnaise fermionic Hamiltonian, which implies that we can solve this problem exactly. Then using the very famous Lieb theorem, one could also show this ground state always live in the vortex free sector, where the order these flux numbers becomes the +1. And especially at this flux sector, this vortex free sector, Hamiltonian becomes even simpler in this way. And then by solving this Hamiltonian, Kitaev found this very famous phase diagram, and the edge denotes the strongly anisotropic limit, and this center is the fully isotropic limit. And also he found 2 distinct quantum phases, and the first one is found around this isotropic point, where this ground state becomes some Gamlis quantum spin liquid, and we call this the Kitaev spin liquid. And this state is characterized by the 2D Ising universality class, and also even more interestingly, this can be driven into the non-abelian topological phase by breaking the time reversal symmetry. Therefore, so this second property brought great interest in this Kitaev physics. Then the other regions, we can find the Z2 topologically ordered gapped spin liquid, where the ground state can be diabatically connected to the toric state. Today, I'm going to focus on this isotropic point with the ferromagnetic exchange interaction. So, however, our scheme can be easily generalized into some anisotropic regime. But today, as I said, I will just focus on this isotropic point. And the isotropic point Hamiltonian becomes this simple form. And here I would like to shortly discuss the symmetry of this Hamiltonian at this isotropic point. First, I would like to define the unitary transformation UC6, which is defined here. And under these transformations, the Pauli matrix just permute in a cyclic manner. So sigma x becomes y, y becomes z, and z becomes x. Therefore, if we apply this global operation on the Hamiltonian, then we expect this x bond becomes y bond becomes z, and z bond becomes x bond. Therefore, we could regard this as some spatial rotation along at the center of this placket, which means that combination of this spatial rotation with this unitary transformation remain the Hamiltonian invariant. And also, similarly, we could define another unitary, use sigma. It's defined here, and this just flip the sigma x and y. So x becomes y and y becomes x, but z remains as it is. Therefore, if we apply this again global operation on the Hamiltonian, then y bond becomes x and x bond becomes y. Therefore, we could consider this as a spatial mirror symmetry along this line. And to choose the mirror symmetry, I will call sigma. Therefore, again, combination with this sigma and u sigma transformations does not change the Hamiltonian. Therefore, this at the isotropic point, Hamiltonian has these two interesting symmetries. And mostly I use these two symmetries to construct some tensor network ansatz. And including these two, we also should consider the translation symmetry and also time reversal symmetry. So these four symmetries require symmetries to construct our tensor network state. And yes, maybe I will skip this introduction to the tensor network part. Yeah, maybe, but I can mention shortly. As we know, the most successful application of the tensor network representation might be the AKT state. So as we know, this AKT state exactly represented by these very simple two tensors. So this the yellow rank 3 tensor is nothing but the Clevishik-Gordon tensor, which if you use the 2 spin 1/2 into the spin 1, and then the red bond is nothing but the I times sigma y, and this is a Pauli matrix. And this very compact and simple representation is the exact representation of this ground state, and we can already know extract many information from this very simple tensor representation. For example, this SU2 matrix is directly says that there is a symmetry fractionalizations in this state. So such a very interesting topological information we can already achieve from this very simple representation. And yeah, so this is one of the most successful tensor network everyone knows. Now I'm going to discuss our trial wave function or ansatz for the Kitaev spin liquid at again this isotropic point. And yes. Yeah, in order to this end, I would like to start with defining the so-called loop gas operator, which is defined here. So we obtain this loop gas operator by summing over all possible loop configuration, and loop configuration of the some local product of the local operators. And to be more specific, on the empty site or hole, we just assign the identity matrix, trivial identity matrix. And then on the loop, and then depending on the direction of the loop, we assign the sigma x or y or z matrix. So here the red bond is a sigma x, and blue bond is sigma y, and yellow bond is sigma z bond. So you can easily recognize it. So by summing over all possible such kind of the operators, we obtain this loop-guess operator. And so for example, the first configuration is just trigger the direct product of the all identity matrix. And then on the second configuration and on the bond, on the loop, we assign the sigma x and y and blah 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 non-trivial operators. And by summing over all possible loop configurations, we obtain this loop guess. And as you can easily imagine, that this is already very non-local because we have to also include infinitely long loops. So this is a very highly entangled and very non-local operator. But with a tensor network, we can realize this operator with a very simple bond dimension 2 tensor. So Qijk here. And yeah, this is the representation, graphical representation for the PEPO or the loop-guess operator, and this the local tensor Qijk. And in this definition, we have another rank 3 tensor tau ijk. It's a bond dimension 2 again, and its non-zero element are written here. So except these 4 configuration, all others are 0. Now let's assign some physical meaning. So let's say on the virtual indices. So for example, on the 0 index, let's think it as no loop on the bond. But for the index 1, maybe the presence of the loop. Then for example, tau 110, so 110 means loop is passing through this x and y bond like this. Therefore, if we contract this Qijk tensor, we may have this kind of exemplary configuration. So 0, 1, 1, 0, 1, 1, 0, 1, blah, blah, blah. Then if we connect the index 1, it always forms just a loop, close the loop, or the hole, the empty site. Therefore, this Qijk makes realized only the loop and hole configurations with the same weight. And the same weight is also important. Yes, so from now on, I'm going to discuss the property of this loop-guess operator. Then the first thing we have to maybe consider is the symmetry of this operator. But as I said, loop-guess operator is kind of the non-local and very entangled operator. Therefore, actually, it's not easy to show whether this operator has some symmetry or not. However, luckily, we have the very compact tensor network representation, Qijk. Therefore, we can show some symmetry. We can show that this operator has some symmetry. And for example, here I will show you shortly this Qijk, this building block tensor, has already this C6 U6 symmetry. So this is the definition again. And let's apply the U6 operation first. Then, as I said, this operation permute the Pauli matrix. So this X becomes Y, and Y becomes Z, and Z becomes X. And then comparing to these two expressions, it looks like this IJK, this virtual indices are permuted. And so this is the graphical representation. This is Qijk, and applying the U on the physical bond will rotate this color of the bond. So now this line becomes the Y bond. So and if we want to rotate just virtual index, just now we can just apply the spatial rotational symmetry. So C6. Then we easily imagine that after the C6 rotations, the resulting tensor is Qijk itself. So Qijk satisfies these simple relations. This guarantees that Qijk is commuted with this symmetry operation. And similarly, at this local tensor level, you can show all these relations. So Qijk also commute with the sigma U sigma, and also this time reversal symmetry. Actually, for the time reversal symmetry, we need additional gauges transformations, but still we can consider this as a symmetry. Then now Qijk also commute with the flux operator, which this commutation relations guarantee that the resulting this non-local loop-guess operator is symmetric under all these symmetry transformations. So now I just showed that this loop-guess operator share all the symmetry property of the Kitaev honeycomb Hamiltonian as well as the Kitaev spin liquid. Yes, and now I'm going to show that this loop-guess operator also guaranteed the vortex free conditions. And I just skip all the details, all the derivations, but here one could easily verify these simple relations. So here, this means that applying the sigma x operator on top of the Qijk is identical to the multiplying V and V conjugate on the two virtual indices. And definition of a V here, and V is the unitary matrix. So graphically, in this simple, it can be written in this way. So this green x is the sigma x, and these two are the V and V conjugate. And similarly, one could also show that show this similar relation for the sigma y and sigma z. And then these three relations are somehow some key relations we found in this study. And using these relations, we can show many things in a compact way. So as an example, let's act this flux operator on top of the loop-guess operator. Then locally we have the distance network. And here, just for simplicity, I just omitted another additional physical leg. And anyhow, the green squares are just the flux operator. So the sigma x, y, z, x, y, z. And just using these relations, we easily see that this tensor network is identical to this tensor network. And then on the bond, we have the V dagger V. And as I said, this is a unitary matrix. Therefore, they are cancelled each other. So we obtain the original tensor network. This means that this guarantees that if we apply the flux operator on top of the loop-guess operator, then we will have just a loop-guess operator without any additional sign or additional phase, and just as it is. And then this is very important because we can make any vortex-free quantum state using this loop-guess operator. So any quantum state obtained by applying the loop-guess operator on top of any random quantum state is always the vortex-free.
So the loop-gas operator is just a sum over all brackets.
Exactly. So yeah.
So this last result is not. I mean, you're just proving it with tensor network.
Yeah, exactly. Yeah. Actually, we noticed that later. After yeah. Actually, this is exactly the same as the. Okay. But I will show you that we can do much more things than just simple that definitions using our tensor network.
So it's a product of your loop operator is the ground state wave function of a toric code mode, right?
No, this is not that one.
The product of your loop.
Yeah, but here, in that case, we have the loop operator is like a sigma or x, z, right?
Yes.
But here, this is a sigma x, y, z, x, y, z, something like that. This is different from the toric code.
But the toric code, the ground state of toric code model is equal weight superposition.
Yeah, exactly. But this is a different, slightly different loop-guess state from the toric code state.
Are they the same ground state or different ground state?
And then we are not talking about the toric code.
Yeah, I know. But you know, in this honeycomb model, you have the A phase. The A phase has a
right. Yes,
state.
yes. But this is not related to that toric code state. Maybe
related.
Related, but if
it should be because you know the ground state of toric code is equal weight superposition of various kind of
I know
closed loop.
Yeah, but here we have to cross another phase transition point. But I don't know what happened here. Yeah. So I don't know whether we have to change tensor, this operator or not by crossing this point.
Yeah, it is possible that there
Yeah,
are
possible.
close relationships.
Yes.
But we have not explored it.
I know that.
Yeah, anyhow. So this loop-guess state Yeah, any Lucas operator guaranteed is the vortex free condition, and now I will show you we can do much more things with this operator. And yeah, here I want to show that this Lucas operator has a Z2 gauge redundancy, which is also required for the Kitaev spin liquid. And as I said, this QIJK tensor has this included this tau IJK tensor. And then notice that the number of the index 1 is always even. So here 0, and here this 3 configuration has a 2 index 1, so it's a 2. So using this fact, you can easily derive these equations. So here G is nothing but the sigma Z matrix, the Pauli matrix. And then here we multiply this G only on the virtual indices. Then graphically we can rewrite in this way. And as we know, this is a kind of the invariant gauge transformations. And then also it has been already known that if such an invariant gauge transformation form a group, we call this invariant gauge group or IgG. And then these characterize the topological character of the quantum state. Then and then I found that this is the only possible non-trivial invariant gauge transformation, and square of this sigma Z is just an identity matrix. Therefore, in this tensor network, host the Z2 invariant gauge, Z2 IgG, which is again required for the Kitaev spin liquid. Now, if this is truly the non-trivial element of the IgG, then it should create the Z2 vortex by inserting this gauge transformation on the bond. So I will show this. So let's insert this G along this line, and then now let's measure this flux on this placket. Then again, same as in the previous slide, we can transform this tensor network into this way. Then again, all other bonds are the V are cancelled. But here we have the sandwich the G, and we easily see that V times the sigma Z and V dagger is minus Z. So we have now a minus sign here, so extra sign here. This implies that insertion of the G create the vortex on this placket. So this is exactly what we need for the what is needed non-trivial element of IgG for the Kitaev spin liquid. So yeah, so far I show you yes, this Lucas operator has this nice property, and especially using this one, we could create any project operator projecting any arbitrary vortex sector interest of yours. So if you can, I will not show you detail, but you can, with a very trivial manipulations, you can make not just this one. You can make another project operator projecting to the like a full vortex sector or like a Vison crystal sector. So you can make a very you can make such a projector using our QIJK tensor and also this G matrix easily. So this is another
This operator G create pair of
yeah, pair exactly. So if you measure the flux here, again we have the minus one. So it creates the vortex these two placket. And yeah, and also if we applied another G, like if you make a string of the G, then it moved this Z2 vortex, and also it also annihilate this vortex. We can manipulate such a vortex using this G matrix. Okay, another questions? So far this Lucas operator looks quite nice. So it shares all the symmetry property of the Kitaev model, and it hosts the Z2 gauge redundancy and also guarantee the vortex preconditions. Now what I want to do is, so I want to prepare some trial wave function by applying this Lucas operator on top of the sum where prepared some initial state, and especially regarding at the rotational symmetry at the isotropic point. I just applied this Lucas operator on top of the magnetic 1-1-1 state, and this is nothing but the classical product state where all the spins along the 1-1-1 directions. And this is just nothing but the classical ground state of the Kitaev model at this isotropic point. Then automatically we see that this resulting prior wave function is nothing but the loop gas state due to this loop gas operator. And the first configuration is just a trivial, just a product state, 111 state. But in the second configuration, and especially on the loop, we applied this sigma x and y in the trivial matrix on top of this magnetic 111 state.
So can you remind us what is the 111 state? Is just the spin pointing?
Yeah, 111 direction.
So,
Just
and you
classical.
work on every side?
Yeah, every side. AB sublattice every side. Since we are considering the ferromagnetic model, this is so yeah, it's a good point. So if we target the anti-ferromagnetic Kitaev model, I just flip the 111 on the B side, and then if we apply the loop gas, then we obtain a good answer. Then due to this loop gas operator, this resulting loop gas state automatically satisfy the most constraint required for the Kitaev spin liquid. As I said, symmetry and gauge redundancy and vortex free conditions. So far so good. Yeah. Yeah, yes, that is a good point. Yes. In fact, the true what we have to really deal with should be like a time reversal loop gas state, and we can obtain this state by doubling the bond dimensions. But all the physical quantity is actually the same with just a simple these configurations. So yes, but to make a time reversal symmetry, we have to add this one. But all other properties are the same. Then yes. Then now we have to check two another things. So first we want to have the critical or Gamnis state, because we are aiming to the Gamnis Kitaev spin liquid. Therefore we need to show whether this is critical or not. And the another one is the radiation energy. And interestingly, even this criticality also can be shown in the analytical or compact way. So to this end, we calculate the norm of this loop gas state. Then I will skip all the details, but using these two relations. So this first one implies that loop gas operator is kind of the Hermitian projector, and the second one is just nothing but the expectation value of this Pauli matrix with respect to the magnetic 1 state is 1 over square root 3, so very trivial one. So using these two relations, one can easily derive that this norm of our loop gas state is written in this very compact way. Here, this gamma is nothing, is the all possible the loop configuration on the honeycomb lattice. Then this LG is the total length of the loop on a single configuration G. And yeah. Then let's look at the partition function of the classical ON loop gas model, which is written here. And here N is some internal degrees of freedom loop, but this is not so important in our case. And then this X is the fugacity of the loop per site. Then just by comparing these two expressions, we easily notice that norm of our loop gas state is nothing but the partition function of the classical O1 loop gas model with a fugacity 1 over square root 3. And actually this model has a really long history, and people study a lot, so we understand many things on this classical loop gas model. So it also has been shown that this model becomes exactly solvable at the same time, becomes critical at this critical fugacity xc for a given n. So yeah, so this is a very nice expression. And then if the loop fugacity is above larger than this xc, then we see these macroscopic loops. And then if it's smaller than this critical one, then we show that only the short range the loops.
Question, comment. Actually, it's a comment. Here you assume the original model, you take isotropic,
Yeah.
Jx equal Jy and Jz.
Yeah.
Actually, if you choose anisotropic,
Yeah.
choose the parameter
Yeah.
inside the
Yeah.
A phase,
Yeah.
there is a loop gas wave function just in the gap phase.
Yes, but
Yeah.
we will not touch on this one.
Yeah, I know. I just
Yeah, I know.
comment this.
We already. Ah, yes, okay. Thank you.
This is anisotropic case. You can't get the gap loop gas.
Yeah. Yes, right. So in another paper, we also studied such anisotropic limit, and then at the time we do not touch this loop gas operator, but we touch the variation parameter I will introduce. Yeah, but yeah, you are right.
So this xc of n is imaginary when you have n greater than 2 or something.
Sorry.
It's not real. It's not a real number.
Ah, so this is true only for the n is equal to and lower than 2.
Lower than 2.
Yeah, lower than 2. And equal to 2. Yeah.
So n equal to 1 is
Yes. So for our case, if we put the n to be 1, then yeah, just critical philosophy is 1 over square root of 3, exactly our case. And then even in this paper, it was shown that this criticality is characterized by the 2D Ising universality class. So this indicates that our loop gas state is also consistent, is characterized by the 2D Ising universality class and critical. So this is also consistent with the Kitaev spin-liquid properties. So far, quite good. So this loop gas state looks nice.
So why do you say it's consistent with the properties of the Kitaev model?
The Kitaev gamma is Kitaev spin-liquid.
Oh, because it's gapless.
Yeah, gammas.
And so how does this Ising universality represent itself in the Kitaev model?
I'm sorry.
The Ising class,
Yeah.
how does it represent itself in the Kitaev model?
Yeah, I mean, conformal information, critical index, critical dimension, scaling dimension.
Scaling dimension?
You are going to show
Then anyways, I will come to show. Sorry, I'm sorry.
I have a question. What is the definition of gap or gapless in classical?
Here?
Yeah.
Yes, there is a very good point. So, in the classical model, and then now this model has a loops, and then if we measure the probability of the loops, you can find at this point. Then this probability is in the gap phase exponentially decrease with the length of the loop. But in the gapless phase, the probability is algebraically decay with the length of the loop.
Two-point correlation.
No. Maybe we can make such a two-point correlation function. But what I know is the probability to find the loop on a bond is it does depends on the, of course, length of the loop, and then this probability algebraically decay with the length of the loop. Yeah, P is like a length. Then this is a gapless, but like then this is the P.
So you are saying the garbage space, all garbage space are actually critical.
Yes, but I don't know what is the critical, how they are characterized. Yeah, but they are NS gapless and critical. Yes. Yeah. We can always see these macroscopic loops.
Sorry. The Kitaev model is a computational model, so why the universality class is 2D instead of 3D?
I will talk you. On the next slide. Yes. Yes, exactly. So you asked why 2D quantum to map to the 2D classical. Actually, Professor Zhang already mentioned this yesterday. But here I prepared a very short slide. Yes, this looks quite strange, but I think this is quite ubiquitous, and you already know a very well-known example, like RK-wave function on the scalar lattice. So as we know, this RK-wave function on the scalar lattice becomes critical, And in this model, we assume that these two different overlap between the two different configuration becomes 0. Using this one, you can see that this norm of this RK wave function is nothing but the two-dimensional diamond model, the partition function of two-diamond model. So the same thing is happening here. And then here, so there is a field theoretical description on this, but I'm not very familiar with this field theory. But anyhow, the low energy physics of the quantum diamond model is well described by this 2+1, the Lifshitz this model. This action is written here. And interestingly, the norm of this ground state wave function is written as the time-independent two-dimensional classical model. So massless free boson, very famous CFT model. And then also all possible correlators, the correlator of the local operator also can be written as the time-independent two-dimensional classical models. So this kind of the interesting things happen in this very special kind of the special class of this theory. And then and this with the RK function, RK wave function of our state also belong to the such a class, and that is called the so-called a conformal quantum critical point. So this is some intrinsic property of the state.
Do you know why this is not called 2D conformal quantum critical point instead of just conformal quantum critical point?
Maybe someone knows. I just found this very nice read paper, but I could not follow everything. So yeah. Yes, this is the reason why our state maps to the 2D classical, and also this is the reason why this can be represented with a very small bone dimension 2 tensor network. And also this RK wave function also can be written in a bone dimension 2 tensor network. So now, as I said, our Lucas state looks nice. So it satisfies all the physical properties of the Kitaev spin liquid. Now the last the piece I want to find is variation energy. And so far I just show you only this paper and the note, the calculations. But for measuring the energy, we need some numerical calculations. And so to measure the energy, I will skip all the details of this technique, but I just used this famous corner transfer matrix renormalization group method. And this is our variation energy with respect to the Kitaev model of this Lucas state, these numbers. But unfortunately, we know that exact energy is here. So our state is energetically very, very far away from the exact one, even though it satisfies all the physical properties. So I want to improve our ansatz, and I want to bring this to around here. And also, as I said, this is the bone dimension 2 state. So if we optimize any bone dimension 2 state, then you will obtain some fully magnetic state with this variation energy. So this is quite much lower than the Lucas state. But now everyone knows this is not better than this Lucas state. So this directly says that variation energy is not everything to choose the ansatz. And also, for your information, maybe 5 years ago, the Philip Corbos already implemented this full update optimization to find the variation of ansatz at this Kitaev isotropic model. Then he found this nice variation energy. However, eventually this ansatz breaks this time reversal symmetry and also rotational symmetry. But that is not surprising because this is obtained by some numerical optimizations. So anyhow, I want to beat this previous result, and I want to come much closer to this exact one. So to this end, I will define another operator, so-called the Dymo-Guest operator, which is defined in similar way. So this is just obtained by the summing of all possible Dymo configurations on the honeycomb lattice. And each dimer is nothing but the sigma xx or yy or sigma zz, so just the local Hamiltonian. Then again, this is again written in a tensor network with only bone dimension 2 with this simple Rijk tensor. And here in this tensor we have another psi zeta tensor of which the non-zero elements are written here. And notice that in contrast to the Lucas operator, it has we can introduce one variation of parameter, and its physical meaning is nothing but the fugacity of the dimers. Then my strategy is prepare the Lucas state and applying the Dymo-Guess operator, and by changing this fugacity, I will see how the energy changes. So it will reduce or not, I will check this. Then maybe people may ask why we choose this Dymo-Guess operator. So here are three main reasons. First of all, it should be fully symmetric, and also it should commute with the flux operator. And also this hosts only the trivial invariant gauge group. So these two guarantee that regardless of how many times we apply the Dymo-Guess operator on top of the Lucas state, it does not spoil the physical property of the Lucas state. So they are all they are kept. So symmetry and gauge Z2 gauge redundancy and also vortex free condition, all they are safe. Then finally, we can also show that this Dymo-Guess operator can be written as the polynomial function of the Kitaev, the Hamiltonian of the Kitaev conical model with an extremely large exponent. So this may suggest that applying this operator may reduce the energy quite effectively.
Sorry, what is a capital H?
It's a Hamiltonian of the Kitaev model.
Honeycomb.
Yeah.
So what's the behavior of sig and with n?
That is quite complicated. So if I don't know how it changes. So if we if we prove something like if they have a same sign or something like that, then this guarantees the exact ground state. But unfortunately, this sign changes, and therefore we could not rigorously show this guarantee the exact ground state. But still, we hope this works.
The summation over n is up to infinite, or
It's the size of the system. Size of the system.
size of system,
Half of the size system. I forgot any of the.
order of size of the system.
Yeah, right. Oh, yes. So with these three regions, I just applied this Dymo-Guess operator. Then before I show you some numerical result here, I just give you a general picture. So left on the hand side is the typical Lucas configuration, which I discussed. Then if we apply the Dymo-Guess operator, it breaks the loop. So you will have this string-like configuration, and it also creates the dimers. And also if we apply one another Dymo-Guess operator, then you will see more, some generalized string-like configuration. But here you can also still see very weird configuration like this. So if we consider the string, then we usually imagine two-end or loop, but we have a very strange configuration here. But anyhow, so we just decided to call this to the string guess state. And yeah, as I said, this looks very ugly, and this configuration doesn't look like a geometric object. But still, what I want to say is, still the pattern of the long-range entanglement is governed by there's a Lucas structures. So Z2 invariant gauge group is still there. So all they share the same Z2 topological character. Yeah.
I'm wondering what is the sign structure of those the string gas state?
Sign. Actually, the initial product state is already complex, so it's not easy to imagine.
Because
Yeah.
I'm wondering, is it possible to evaluate observables using Monte Carlo sampling? Is that possible? Or no?
I'm not familiar with this Monte Carlo.
Like if you are on a valence bound basis, you can, for example, easily compute the observables and overlaps and so on. But the thing is that we are afraid of sign structure.
But
on those overlaps. Yeah, I'm sure.
I think it's a fully complex wave function, so I don't know whether we can find some well-defined transformations that can make it sign-free wave function. I'm not sure. And yeah. So here, so as I said, the Dynamox operator has one single variational parameter, and here I prepared the first order string gas ansatz. Then this is the variational energy, and this is the variational energy as a function of the variational parameter phi here. And this leftmost, this data is for the loop gas state, and as increasing the fugacity of the dimers, you can find really drastically the energy is reducing. So this is quite surprising. And then so this looks and this red solid line is the exact energy. But here what we have to additionally check is that the criticality of this string gas state. So all other the physical property can be is kept. They are kept, but we don't know whether these are still critical or not. So again, we try to calculate the norm of this string gas state, but now this is not exactly solvable model. Therefore, we just apply the loop optimization of the tensor network renormalization group, and then we try to extract the conformal data of the norm of the string gas state. And then this is the C is the central charge, and all other three are the largest scaling dimensions, and as a function of this phi up to this point. So all they are still belonging to the Ising universality class. So we can safely regard this our state still is a good candidate for the Kitaev spin-key. But unfortunately, on this right hand side, this loop TNR does not work at all, and all other tensor network renormalization group method does not work at this region. So I could not resolve this part, but at least at this point, this can be actually you can show exactly map this to the loop gas state. So at least this point should be the true exact 2D Ising universality class.
So first, what do you mean by it doesn't work? The team looking at doesn't work.
So if we draw the like a RG step, and then if we draw the central charge, then maybe this part looks like and then diverging over that, and then we have some stable region, but this part I never see such a stable region. So it always diverging and dying, and so I did not see some converged behavior.
Do you use a tensor network renormalization?
Loop TNR.
Loop T?
Yes. Actually, the usual tensor TRG does not work. I mean, the short range entanglement should be removed for these calculations. Yes, so here we obtained a quite nice variational energy, this one, and then I checked all they still belong to the Ising universality class. However,
do those things work for the loop gas state without projection?
I'm sorry?
If you apply loop TNR to the...
Yeah, perfectly. Yeah, this is the loop gas state.
Oh, that, yeah, you're right.
Yeah. Yes, so I also checked the numerically, then it perfectly works.
So do you also calculate the correlation function and Tensor function?
Actually, no. Actually, I expect this already guaranteed the criticality of the state. So I did not calculate the correlation function, but we extract the correlation length from the transform matrix calculation. I will show you later. Yeah, so just by changing only one variational parameter, we obtain quite nice variational energy. But still, we did not beat the previous result. So since we are computational physicists, we should challenge.
The parameter theta here,
Yeah.
you're just using a tuning parameter.
Yeah.
Is it possible to regard it as a variational parameter?
Yes. Actually,
What's the optimum value of the phi is
I'm sorry.
you will get? If you regarded phi as a variational parameter.
Yeah, here I regard it as a variation parameter. This is how I change the variation parameter phi.
Okay.
And then this is just the measured energy.
I see.
Yeah, yeah.
I see. Sorry.
In fact, this is actually identical to your deformed wave functions. I realized yesterday z and hx sigma x. Actually, this is the Dynamo's operator I consider. So this is the in my case phi. Yeah. The between these two numbers. Okay, let's say these two h and h
Equal.
Yeah, equal. And then if you change this ratio, that's exactly our phi. Yeah.
I see.
Yes. So now, and now I applied another Dynamo's operator. So now our answer becomes one dimension 8 state. And now I will say this the second order string gas state. And notice that the building block tensor has only is quite sparse. So only about the 10% of the elements are non-zero and 90% are zero. And this is quite compact tensors. Then this is the energy landscape as function of these two variational parameters. Then I found out this region gives a quite low energy, but here I found the lowest. And then I performed another scaling as a function of the chi in the CTMRG. Then this is the scaling behavior of the energy, and this is the best energy we achieved. And then this is only 0.00% higher than the exact energy. So this implies that our loop gas state and also string gas state represent the exact Kitaev spin liquid, both the qualitatively and also quantitatively very well. And also notice that our state is only written in a spin language. So I never referred the Mariner formula. So this is completely written in a spin language. So I don't know. To me, the Mariner formula is too difficult to intuitively understand. But this is a very simple and gives a very simple picture in the spin languages. Then, unfortunately, the bond dimension 8 is too large to apply the loop TNR. So I could not apply I could not extract this conformal data directly. So in order to show the criticality, we extract the correlation function. I'm sorry, this is inverse of the correlation length. And then this is the 5 largest the correlation length as a function of the inverse of the chi. So all they look like diverging. So this also can strongly suggests that our state is still critical. And also we can see such signatures from the convergence of this environment tensor in the CTMRG. So if we try to measure our answers with the CTMRG, then convergence is extremely slow. So this quite shows some signature of some criticality of the state. And recently, we also studied some Kitaev model on the star lattice, but I think I will give a presentation for this on the symposium. Then, I will summarize the talk. So here in this study, we propose the loop gas and the string gas state, which belong to the family of the Kitaev spin liquid, and they we show they have this property and blah blah blah. And here, but maybe people may ask why we need this answer, because Kitaev model is exactly solvable. However, we know that in the Kitaev, real Kitaev materials such as the alpha ruthenium chloride, other interactional perturbations exist, and they are quite important, such as the Heisenberg or gamma interaction. So if such an interaction exists, then this Majorana representation doesn't help much. So we hope our loop gas and string gas state are quite reasonable and good starting point in the numerics, even in the analytical understanding of this generalized model. And then also I would like to, so we hope that the loop gas state may play a role of this AKT state in the Haldane phase. So as we know, AKT state is extremely simple, but still it possesses it shares all the physical property of the Haldane state. So only just understanding this AKT state is enough to study this Haldane phase. So I expect the loop gas state can be can do the same things, and we can also we can make many interesting questions related to this loop gas state. And then finally, I also want to make a relation between our string gas and also some Majorana fermions, because we usually expect that some end of these strings, Majorana fermions or another topological particles are dangled. But and so from another study, I also found such a relation, but not directly. So I'd like to find some nice connection between these two pictures from our answers. Okay, thank you very much. Yes.
So could you go back to the slide where you showed the energy versus the phi work phi?
Yeah. Oh. Yes.
Yes. Maybe I just missed, but this figure shows the minima for 0.224 pi, which is very close to 4 pi over 4.
Yes.
Is it just a coincidence, or do you have any reason?
I don't know. Actually, I hoped this to be 1/4. but anyhow, I found the lowest at this point. And I did not find any physical meaning or physical reasons.
I have two questions. One is this left figure is just confirm. No, sorry. This one is confirm all finite size spectrums.
So this is
Oh,
a
central charge.
Central charge and scaling dimensions.
Blue one is a central charge, and
Central charge.
the other colored ones is scaling dimensions.
Scaling dimension. For the IC CFT, we have 1 epsilon and sigma primary field. Are you also are you seeing this primary field?
Yes.
Which corresponding to
I forgot.
The red one is a sigma.
red one is sigma.
Red one.
This is sigma.
One X.
Yellow one is epsilon.
What about the green one? The top
Green one is 1 plus
1 plus.
sigma.
1 plus sigma. Okay. The second question is, have you considered the presence of magnetic field?
Yes, but yes, right. Okay, maybe I have to show this. Yes. Actually, we made some speculations in the presence of the magnetic field, and we also did some variational calculations. And then, so if we look at the loop gas state, then we usually we have 4 different magnetic state on site.
Yeah.
So sigma x and sigma y, so sigma z, and then loop gas state is made of the same weight of these 4 different configuration. But if we consider the 111 magnetic field, then we naively expect that this has the larger weight. Then maybe energy may be reduced, right? So so in the presence of the magnetic field, we can introduce some variational parameter like a c. Then if the magnetic field is finite, then we can
magnetic field is only apply a one direction. Okay.
Yeah.
One direction. Or just one. Okay.
Yes. Then we naively expect that this maybe if we make a c to be larger than 1, then energy might be reduced. So yeah, and actually we find we did such a variational calculations, and then only if we look at only the loop gas state, if we change this c larger than 1, then this state is entering into the gap phase, and then it looks quite consistent.
Good,
yeah, but still we did not. I could not find the well-defined non-abelian signatures. There might be the gap is too small. So
if you break the time reversal symmetry, somehow, so there's a small gap open up. And then you should have a finite Chen number.
Yes, right. But
but in your case, I don't know how to calculate Chen number because in this spin representation.
But in the symposium, I will show you another one. So I found the non-abelian characters from this ansat with from the entanglement spectrum and also entanglement entropy. So I will show you later. But at least for this honeycomb with the magnetic field, I could not find such signatures. So I mean, story looks nice, but I cannot rigorously show whether this becomes the non-abelian state or not.
You said you calculate the topological entanglement entropy, the correction. You got a log 2 correction?
Log. Okay, maybe. I will shortly show you this. Yeah. So this is actually Kitaev on the star lattice.
Oh yeah.
And
here has the same state.
Yeah. And so this is now the model parameter phi. This is the variation parameter. And this side we expect a non-abelian phase.
Yes.
Then this is the topological entanglement entropy for the vortex. And then this vortex shows the log scale to 2. This is consistent with the topological entanglement for the sigma anyons in the topological Ising field theory. So again, our picture also describe the non-abelian and abelian picture very well. But maybe I will discuss these details.
So a related question for those family of states you talked in today's talk. It looks to me it all belongs to the same phase. There's no phase transition after the projection. So then, is it possible to extend that to a big family of states? For example, at least cover torical limit, or maybe cover Kitaev Heisenberg, or K-gamma model?
That's exactly what I'm doing, but maybe not the analytical this way. But I'm using the numerical optimizations from our ansat by including the perturbations. But this clear picture may not be, made in such a generalized model.
Just add the definition of the loop gas operator.
Okay.
Yeah. So here the weight for each diagram is
Same.
same.
One.
How about the case for different weights?
Yeah, then we will enter into the maybe another phase. I mean, then that exactly. Okay. Here is critical. Oh yes. Oops. Sorry. Yeah. So now we are at this point. But if we change this weight, then we may enter into this one, but we may enter this one. But that model may not be exactly solvable. Only this point is exactly solvable point. So maybe that can be gapped or gapless, but we should show this in the numerics. Yes?
So I think I missed a step in your logic. So you have this QLG operator.
Yes.
And you act on the 111 state.
Yes.
And that is some trial state.
Yeah.
So what is the motivation? So I understand the QLG has some very simple tensor network representation.
Which one is this?
The QLG operator.
Ah, yes. Yeah.
But so
motivation is simple. So Lucas operator itself shares all other physical properties like symmetry and gauge redundancy and vortex free condition. And if we apply these two, then resulting state should satisfy all these the properties. And yeah, that's the motivation.
Why you cannot extract the conformal data from the second ansatz using loop TNR?
Yeah, so in that case, the bone dimension is 8. And then, I don't know, loop TNR has a requires quite large computational complexity. So, and also this state is quite, very highly entangled. So we need really huge bone dimensions, I think. So the loop TNR always does not converge, and it shows a really weird the flow. So I could not extract the conformal data.
Can I ask this question? In your string gas gas picture,
yes,
it seems there exists some isolated dimer.
Yeah.
And does it mean the excitation in such kind of states will have some has some additional elementary excitation? For example, the dimer, one of the spin, one half in the dimer flip, and it will change to a triplet state, spin 1 excitation.
But now this model does not have the SU2 symmetry. So this spin triplet singlet, is it well defined?
It can emerge at certain conditions.
Okay, but okay.
If you have such kind of isolated dimer, so when such kind of state.
But this is not that dimer. This is not the singlet. This is not the singlet. This is only the. Okay. Okay. Maybe I made one state. I site and J site. Dimer means this configuration. This is the product, two different or gamma. Yeah. This is XX or YY or ZZ. Yeah.
Why you call it dimer?
It looks like a dimer. just the two-side object. So I just call it a dimer. Yeah, this is not related with this singlet formation. Actually, this is the same as your.
What kind of situation?
Here?
Yeah. What kind of excited states corresponding to this state? If you flip one spin, or this state will becomes a finite magnetic moment. You have a finite moment there.
Resulting state is non-magnetic.
Yeah, I know. The excitation, local excitation.
Okay.
Local excitation. Yeah.
I never thought about, so I cannot.
because in Kitaev B phase there's only this Z2 meson and Majorana excitation. And no other type of elementary excitation. But here, in this in your configuration, it seems to me, I'm not quite sure. It seems to me there are some additional excitations.
Okay, I see. But I cannot answer.
Okay, I can consider for me.
Okay.
So, can I see from your result you showed for a critical wave function there is sometimes low local correlation to the contamination. So this means perhaps this finite one dimension can represent this wave function very well.
I'm sorry, I cannot.
So
I didn't.
I mean, from your result, can I understand? So for critical wave function, there is, because in 1D we usually expect there is a log L correlation.
Yes.
For in 2D there is no this log L.
But that is not all the case. If you have the finite Fermi surface excitation, then we have a log correlation.
But in case like this, there is no log L corrections. That means the finite perhaps with finite D can
might represent. Yes.
So another question, maybe I have missed
Yes.
So what's your final energy compared with Cox result?
I did not compare, but anyhow much lower. much lower. This maybe. So final. Sorry. Final. So this is the Philip Corpus. My final one might be between these two.
Okay. So what's the one dimension for?
8. But Philip Corpus they use a 7.
So
But your result is much lower than the corpus, right?
If I remember correctly, yes. Philip Corpus, their result, only if I look at only the energy, then error is like a 0.01%, something like that. And ours,
not much lower.
Okay.
Do you do like an extrapolation, like as for example?
Actually, I did not. So I just picked this one. Maybe if I do the extrapolations, maybe I could.
Yeah.
But only lowering energy is not my final interest. So if
important thing is that we have a much smaller number of parameters compared to the corpus calculation.
I don't know. But if you look, I don't know. So if you look at the symmetry, then I cannot compare these two, right?
That may be a more important aspect. Symmetries and all of that.
Actually, this energy, I never expected this energy. This is quite lucky to me. So, this is scheme. This kind of the variational. Direction was my interest, and luckily energy, I obtained quite nice energies. So, anyhow.
Actually, I have a suggestion. I think compare with the ground state energy density is just one way to check whether how good your theory is. But here you can also calculate the overlap between your state with the exact wave function, because we already know at this point this exact soluble model will have an exact wave function.
But how can we write the exact state in a tensor network representation? I cannot. This Marana fermionic, this.
With additional axes.
Yes, with additional axes.
Right. I know what. But anyhow, physically we cannot distinguish these two, physically, right? So that's the point I want to.
with d equal 8 with perhaps
Yeah.
without this symmetry, I think the energy will be low and low.
It must be by
Yeah,
definition.
Actually, I forgot to mention that. Here I choose different way to improve our loop guess, but maybe Kaneko-san will say about this. Numerical optimization.
Yes, but it is not really the variational. Strong in a strong sense variation.
But anyhow, this also I have to say that if we start the simple update with the imaginary time evolution upon this loop guess state, then it really converges to a very nice answer. Still, my state and is very competitive energy both have. So so this also answers is help to help these optimizations, even in numerics way.